Hello everyone. Today we are going to talk about basic architecture of a computer. So first we are going to talk about topics that are included in computer fundamentals course. So we will talk about number systems, Boolean algebra, basic architecture, central processing unit, I/O and memory organization, peripheral devices, data representation, operating system, networking, virtual memory, file systems and elements of programming. Number system and Boolean algebra, these topics are covered in digital electronics. So we are starting from basic architecture. So if you are talking about basic architecture of a computer, the first major component of a computer is its CPU, its central processing unit. What is a CPU? CPU is a part of a computer which takes data, processes this data and produce desired result. Just like, for example, A is equal to 10, B equal to 20, CPU takes this data. We have to perform an operation A plus B. CPU performs this operation and produce desired result. So basically, if you are talking about CPU, a central processing unit, it has three components. First is register set, second is ALU, and third is control unit. First is register set. Why we require a register set is, suppose we have to perform an arithmetic operation, that is, suppose we have to perform 2 multiplied by 3. Now, if we are talking about basic CPU architectures, basic microprocessor architectures like 8085 or 8086, then these microprocessors did not have multiplication functions. So how multiplication took place in these microprocessors was, suppose we have to multiply 2 into 3, so it will take place in form of addition. That is, first it will add 2 plus 2, produce this 4 which is produced. This is an intermediate result. Then again 2 will be added and it will produce final result 6. So we are having this intermediate result. We require this intermediate result for our operation. So where will this intermediate result go? So for this we require a memory block inbuilt within the microprocessor or central processing unit. These memory blocks are known as registers. Okay, so every CPU have some set of registers. Second one is ALU, arithmetic and logic unit. Okay, so why do we require arithmetic and logic unit? We performed 2 into 3. This operation, when we provide this instruction to be executed, this operation is performed by arithmetic and logic unit. So arithmetic and logical unit basically have components which are capable of performing different operations like multiplication, division, addition, subtraction, modulo, remainder fetching, AND operation, OR operation, so NOT operation. These arithmetic and logical operations and much more operations, these are performed by ALU. Third and most important part of a CPU is control unit. So basically control unit is just like human mind. Just like our mind controls movement of our hands, our eyes, every movement in our body is controlled by our mind. In same way, Each and every operations that is to be performed in a CPU is governed by control unit. Control unit gives instruction to ALU for performing a particular operation. Suppose we have to perform A plus B. We give this instruction to a CPU. In CPU, this instruction goes into control unit. Now, control unit will give command to ALU to perform this operation. Okay. Now, in turn, ALU will contact registers to get necessary data, that is A and B, and store the result. This storing result is also takes place in register. Okay, so this was a basic view of CPU. Now we are going to talk about a basic architecture of a computer. So in basic architecture of CPU, we are having following components. Okay, first I think we should talk about how instructions are executed in short. Okay, so whenever we give any instruction, wait a minute. Okay, so whenever we provide any instruction to a computer, just like A plus B, this instruction is not understood by a computer. Computer understands binary. So basically we give instructions like this: add A comma B. This instruction is provided in terms of binary. Suppose code for add is 1100 and code for register A is 010, code for B is 011. So this is our instruction which is to be provided to a computer for execution. Okay, so how our computer operates: when we give a instruction in this format, first computer will fetch this instruction from a memory. This instruction will be stored in a memory. Our computer will fetch this instruction. Then our computer will decode this instruction by dividing this into different parts. That this means add, this means A, this means B. Our computer will decode this. Then our computer will execute it with the help of CPU, ALU, control unit and registers. So coming to our basic architecture. So when I talked about this instruction in binary format, this instruction or this address, this is stored in a register which is known as MAR, memory address register. What does it do? It stores the address of instruction which is to be executed. These orange lines which we are watching, these are a common bus. This is a common bus. What common bus does it? This MAR will place data on this common bus, and this common bus will transport this data to different parts. Now after fetching the instruction in binary format, this is placed on a common bus. Now this common bus, what does it do? It provides this data. If there are operands in this data, just like add A plus B, A and B are operands. So A and B will be having some data, just like suppose A is equal to 10, B is equal to 5. So this data will be gone to register A. Register A is known as accumulator. Accumulator, this is an inbuilt register which is used in arithmetic and logical computations, and register A is the register which stores the result for any operation. Now second is DR. DR means data register. So suppose we write add 2 plus 4. So this data, one of the operand goes to accumulator, second operand goes to data register. Now these register A and data register are connected to ALU. So suppose we have written add A plus B. So ALU, we discussed it earlier that ALU performs the arithmetic and logical operations. So ALU will perform operation on this data and again place it on common bus. Now, first thing that happens is whenever we place an instruction, it goes into instruction register. What instruction register does it stores the instruction, and then by the use of a decoder it is decoded and it is provided into timing and control unit. Now control unit will direct ALU or any other register or any other part to perform operation as required. Okay, so timing and control unit have different components, different pins coming out of it. So this is just like memory address register, out enable. Okay, so first of all we are going to discuss about out enable and load pin. What is out enable and load pin? Suppose we are talking about this is PC is program counter. Program counter contains the address of next instruction to be executed. Now, so suppose we have a memory block. This is a memory block. Okay, this has different parts. Suppose we are talking about address. Its address is 1000, it's 1001, 1002, 1003. This is a memory which have instruction. Now instructions are stored in binary format in these memory locations. These all are instructions. Okay, so what happens first this is our IR instruction register. Instruction register will fetch this instruction. Decoder will decode this instruction. Then it will be executed with the help of different instructions, different registers. Now we are talking about timing and control unit, and as we saw, different registers have two pins. Just like suppose we are talking about program counter first. Okay, so what program counter does is program counter have address of next instruction to be executed. Just like when we are executing this instruction, then program counter will contain address of next register. Okay, when our CPU is executing this instruction, then program counter will contain this address. Okay, so it basically contains the address at which instruction is present. So every register, just like program counter, it has two pins. One is OE, which is known as out enable. Second is LD, which is known as load pin. So OE or out enable, it activates this register to transfer data outside. Okay. Now second pin is load pin or LD pin. What does it do? It helps the register to get data from outside. When load pin of program counter is high or is 1, then program counter will get address of next instruction. It will fetch address of next instruction, just like a read operation. OE out enable is just like write operation. It will write data into some other register or some other memory location. Okay, so we were discussing about these are the basic building parts. I skipped some parts just such as R1 and R2. These are temporary registers. Program counter I just discussed. Program counter contains the address of next register to be executed, next instruction to be executed. There is a stack pointer. A stack is basically a memory block which have some memory, and we will discuss stack later. Okay, now we will talk about instruction format. Okay, so first, instruction format. We know what an instruction is. Instruction is basically the tasks that we give to a CPU or a computer to perform. Okay, so an instruction has basically two parts. One is called opcode, second is called address field. Okay, so suppose we are starting from a memory block. Suppose we have a memory of 4096 into 16 bits. This is the size of our memory. What does it mean? It means suppose we are talking about 4096 into 16. So 4096 into 16, that means there will be 4096 number of memory locations starting from 00000 to 4096. Okay, and each and every memory location will contain 16 different bits. Okay, so 4096 words, and every word consists of 16 bits. This is the meaning of this. Okay, so if we are having a memory of 4096 into 16 bits, so to address these many locations, how many address lines will be required? We need to calculate this. So we will calculate this by taking a basic example. Suppose we have 4 memory locations. Okay, so these 4 memory locations in binary format will be 0001 1011. So how many memory lines do we require? We require just 2 memory lines. See, this is 1, this is 2, this is 1, this is 2. So in 2 memory locations, 2 address lines, we can address all memory locations. So if number of memory locations is m, then if we express this m in form of 2 to the power n, then n is number of address lines. Okay, now talking about 4096. So 4096 is basically 2 to the power 12. So we need 12 address lines. 12 address lines, that means we need 12 bit for expressing the address. Okay, so that's why we are using 0 to 11 bit of a 16 bit register as address line, address bit. Now after using these 12 bits, we have left 4 bits. These 4 bits are used for storing opcode. What is opcode? Opcode is operation code, that is for add we have some opcode 1000. For multiply we have some opcode 1100. So this is known as opcode. Opcode is operation code, means operations in binary format. Okay, so since its length is 4, that means this total number of combinations possible is 2 to the power 4. 2 to the power 4 is 16. So that means we can have total 16 different combinations for opcode. So does it mean that we can have only 16 operations in a computer? No, we will discuss it. We will come to it later. Okay, now okay, so suppose we are having okay, now we will discuss about this field, basically 0 to 11. This field contains, this can contain directly operands, that is directly it can contain data, that is add 4 plus 6. This field can contain directly 4 and 6, that is called as immediate operand. Okay, this can contain address of a memory location. This can have address of a memory location, just like it has 1000 written in it. Now if we go to, suppose this has 1000, now we will go to this particular memory location 1000, and this will contain the data. Suppose it is containing 3 or 4 or something. This is called direct addressing. Now there can be another case in which this is the address of a memory location which contains address of another memory location which contain the data. Okay, this is known as indirect addressing. Okay, so how do we differentiate whether it is an immediate operand or direct addressing or indirect addressing? So what do we do is we provide this last bit as I. If I is 0, then it means direct addressing. If this is 1, then it means indirect addressing. Now only 3 bits are left for operation code or opcode. Now that means just 8 operations can be expressed by this field. Okay, so let us discuss a bit more about direct addressing and indirect addressing mode. For direct addressing, this bit is 0. Suppose we have an instruction 0 add 457. What does it mean? If this is direct addressing mode, Okay, 0 means direct addressing mode. So that means 457 is the address of memory location that contains data. So we will go to 457. 457, this is 457, this has operand. We add this operand to content of accumulator and store the result in accumulator. This is direct addressing. Okay, now coming to indirect addressing. For indirect addressing mode, the value of this bit is 1. Okay, so 1 means indirect addressing. 1 at 300, that means 300 will not contain directly the operand. This memory location contain directly the operand, but here in indirect mode this will not contain directly the operand. We will go to this location. This another memory address will be present in this location which will be having operand. Now this operand will be added to content of accumulator and this is stored in accumulator. Now this address which contains the operand, this is known as effective address. Okay, so in case of direct addressing, effective address is the direct address which is provided here. In case of indirect addressing, effective address is, this is not the effective address. Effective address will be the address which is present in this memory, this particular address, this memory location. Okay, now talking about basic registers that are required in a computer. So for the configuration that we took, 4096 into 16, there will be a data register, DR data register, which will be of 16-bit. Okay, there will be an address register. As we saw, 12 address lines are required for addressing the all data, all memory locations. So 12, it will be of 12-bit size. Okay, there will be accumulator which will be of 16-bit, instruction register 16-bit, program counter. Program counter basically contains the address of next instruction and address is of 12-bit only, so it will be of 12-bit. Okay, there will be TR, that is temporary register, which will be of 16-bit. Input R, output R, which are of 18 bits. These are basic registers present in a computer. Okay, now talking about instructions, we discussed instruction. We basically divide instruction code into 3 basic parts. One is memory reference instruction, second is register reference instruction, third is input output instruction code. So memory reference instruction code is when these bits contain the address of a memory location which contains operand. So like we discussed here, this memory locations, this was memory reference instruction. So it can be of 2 types, direct address, indirect address. If this bit is 0, then direct address. If this is 1, then this is indirect address. Now talking about second type, that is register reference instruction code. So register, in case of register reference instruction code, this type of instruction does not require any memory address. Such as example of this is add R, add A suppose, or add B. So this means it contains a register name here. This register will be added to, the content of this register will be added to content of accumulator and this will be stored in accumulator. Okay, so basically these 12 bits are unused in this case because there is no memory address. So in case of this, in case of register reference instruction, these 4 bits are fixed. These 3 are 111 and this is 0. These are fixed. Okay, and rest 12 bits are used for operations, for opcode. So basically in this case we could store 8 operations, but in this case we can have 2 to the power 12 operations. Okay, in case of input output instruction code, these last 4 bits are 1 fixed, just like here these 3 were 1, this is 0. Same way these 3 are 1 and this is 1, and rest 12 bits are used for opcode. Okay, these are 3 kind of instruction formats. Now we will come to how CPU identify, how control unit identifies any instruction. So what does CU, a control unit, do is it checks bit number 12 to 14. Bit number 12 to 14 in case of memory instruction, this contains opcode except 111. In case of register reference, this is 111. In case of input output, this is 111. So it checks bit 12 to 14. If this is not 111, that means it's a memory reference instruction. In that case it will check B15. If that is 0, then it is direct address. If that is 1, then it is indirect address. If bit 12 to 14 are 111, then it will again check bit 15. If that is 0, then that is register reference instruction. If that is 1, then that means input output instruction. It will take necessary action to perform these instructions. Okay, so how does a CEO of basic computer takes instructions? These 0 to 11, these are provided directly. These can be address, these can be opcode. 12, 13, 14, these are important. First, these are decoded by 3 into 8 decoder. Now these 8 are provided at control unit. This 15th bit is I, which is either 0 or 1. This in case of memory reference instructions, this address is direct address or indirect address. In other case, if it is 0, then that is register reference instruction. If that is 1, then this is input output instruction. Okay, sequence counter counts the sequence or counts the timer. Okay, we will come to this architecture later in central processing unit in detail. Okay, so this is a basic computer, design of a basic computer. What does it require? It requires a memory unit, it requires registers, it requires flip-flops, decoder, 16-bit common bus, CUL and ALU gates, address and logic gates, and this is how we are going to connect it. This is the basic computer design. Okay, so that is all about basic architecture of a computer. In next class we will discuss about central processing unit in detail. We will discuss about ALU, control unit, stack and other parts. Okay, so goodbye.